Okay, so that completes part 1. Now we'll move on to part 2, which is nuclear structure. So this is the second part of 7.1. Now, for exam purposes, nuclear structure. The first thing that you need to know, and it's probably not in the notes, is the definition of a nuclide. Okay. So let me just show you. Firstly, the definition of a nuclide. This is not mentioned in the notes, but a nuclide is defined as an atomic species. Okay? Is defined as an atomic species that can be, okay, it is there in the notes in the definition for nuclide. A nuclide is an atomic species that can be represented by or characterized by its proton number. Okay? This here is its proton number and its atomic number or its nucleon number. Okay, so this here is the nucleon number. What's a nucleon? A nucleon is a collective name for protons and neutrons. Okay, so a nuclide is an atomic species which can be represented or characterized by its proton number, which is the number of protons, and the atomic number or nuclear number, which is the collective name for protons and neutrons. And X here is basically telling you what element is this species. Then there's the definition of isotope. Isotopes are basically variants of the same atom or element with a different number of neutrons. So as long as the proton number is the same, the species would be the same. But if the number of neutrons are different, then there would be isotopes of each other. Okay. After that, there's a description of nuclear interactions where, as I mentioned before this, there's a definition of the strong nuclear force and how it acts. So the strong nuclear force, like I mentioned, exists between nucleons at a distance of less than 1.3 femtometers. So if in the nucleus, all the nucleons are separated by 1.3 femtometers. If the nucleons are closer than this, then the strong nuclear force becomes repulsive. If it's further than that, then the electrostatic force comes into play as the nuclear force drops suddenly to 0. Therefore, the nuclear force makes sure that the nucleons are 1.3 femtometers apart. Okay? And a femtometer, like you know, is 10 to the power minus 15 meters. So yeah, that completes section 1. Now we'll move on to section 2, radioactive decay. Okay, 7.2 is radioactive decay. So firstly, defining radioactivity. Radioactive decay is the spontaneous and random disintegration of a parent nucleus to form a daughter nucleus. Why is it spontaneous? Because it happens regardless of weather conditions, temperature, pressure, etc. It's also independent of whether the radioactive substance is combined with other elements in a compound. So also you do not need an external trigger for radioactivity. For example, in nuclear fission you need probably an external trigger like a neutron or a proton, but over here it happens on its own. It's random because there is no way of predicting when exactly is a particular radioactive nucleus going to decay at any one point of time. It happens in a random fashion. So that's why it's random. However, it is possible to determine the probability of decay of any particular nucleus and we'll come to that later. So why does radioactivity occur? Because a parent nucleus is unstable and it wants to get rid of a certain component in order to make it more stable. So on page 7 there is a description of spontaneous and random. And then there are three basic types of radioactive decays that we'll talk about. There's alpha decay, you have beta decay, and gamma rays. So alpha and beta are particles, gamma is an electromagnetic wave. Okay, it's a photon. So page 8, you have a description of what these, there's a table in 7.2.2. You have a table describing the nature of these three radioactive substances, radioactive components, and you also have, so this is basically a summary that you can go through with the students. Some important features over here are the relative sizes and the ionizing effects. So alpha particles, for example, can ionize much more easily than beta or gamma because it has more charge. But so therefore, the more ionizing it is, it's more harmful because when something is more ionizing, it can combine with molecules within your body like the DNA and produce free radicals. But also it should be taken into account that the penetration range of gamma rays is way more than alpha or beta. So alpha, for example, can only be stopped by just a few sheets of paper, whereas in order to stop gamma rays you need several centimeters of lead. So this is something you want to make sure that the students understand. So all three forms are harmful in their own ways, but these are alpha particles, for example, are harmful at close range. Gamma rays are harmful at long ranges as well. Okay, so alpha decay is basically when an unstable nucleus, okay, comes down to a stable state and gives off a helium nucleus. The helium nucleus basically is the alpha particle. Now, why am I drawing this kind of a notation is basically showing the nuclear energy levels. Now, just like at atoms, just like electrons and atoms exist in different discrete nuclear energy levels, the nucleus itself also exists in discrete energy states. So this nucleus, for example, is at a higher energy state and when it gives off an alpha particle, it comes down to a lower energy state, which is more stable. Okay, mind you that this state may not be the ground state of element Y. Element Y might have another state over here. This might be the ground state. So when X decays by giving off an alpha particle and comes to this state, Y might come down to a ground state, okay? And in the process, when this nucleus comes from an unstable state to a stable state, it will give off a photon, okay? Now, what kind of a photon? The difference between atomic energy levels where electrons exist is of the order of a few electron volts, and therefore the photon that is given off has lesser energy. It's somewhere within the visible light region. That's why we can detect it in the absorption and emission spectra. But in this case, the energy of this photon is of the order of a few mega electron volts. So in the electromagnetic spectrum, these photons have a much higher energy, and therefore these photons are gamma rays. Okay, so in this fashion you can see that alpha decay will sometimes be accompanied with, will almost always be accompanied with gamma rays as well, when daughter nucleus falls from an excited state to a ground state. Okay, so that's how you have gamma rays being accompanied with alpha particles. Now, the element X over here might fall to the excited state of Y over here, or it might also release an alpha particle by giving off an alpha particle over here. It might also reach the ground state directly. So, and this Y might have a few states, but all of them will be discrete energy levels. Therefore, the alpha particle which gains energy, the difference in energy between these two states is the energy gained by the alpha particles. Therefore, if you see the spectrum of alpha particles, right, you will see that the alpha particles have a discrete have discrete energies. Okay? Okay? And similarly, gamma rays, the only way in which gamma rays are emitted is when an excited nucleus falls to a ground state. And since these states are discrete, therefore gamma rays will also have discrete energies. Okay? So if you see the spectrum of alpha particles and gamma rays, both of them are discrete spectrums. Now this here and this here is a proof of existence of discrete nuclear energy levels. Okay, so this is important for the exams. Okay, so the proof of the existence of discrete nuclear energy levels is the discrete energy spectrum of alpha particles or the discrete energy spectrum of gamma rays. Okay, now that covers alpha and gamma. Now let's talk about beta particles. So what happens in beta particles? Beta particles are of two types, beta negative or beta positive. Okay? Beta negative is simply an electron. Beta positive is the antiparticle of electron called a positron. It's of the same size of electron, but it has a positive charge. Now, what happens is, if in a nucleus there is an excess, if there is an excess of neutrons, a neutron might then disintegrate to form a proton, okay, and to balance out the charges it will also give off an electron. Okay, so you can see this happening in on page 8. It starts at the bottom of page 8, beta negative decay, and you can see that a neutron over here, okay, disintegrates to form a proton and electron. Okay, electron has zero mass as compared to protons because it's around the size of a, well, it's about 9.1 times 10 to the power minus 31 kgs, which is way less than that of a proton. So, okay, so now you have this. Okay, so it gives off a proton, and to balance out the charges, it gives off an electron. So how does that work? Let's say X was at this state. Okay, when a neutron changes to a proton, your proton number changes, and therefore your element will change as well. Okay, so from a higher energy state, it comes to a lower energy state, and it will give off a beta negative particle. Well, in this case, yeah, it will be a beta negative, right? So because one neutron has changed to a proton and a beta negative. Okay, so now that it has come to from a discrete energy state to another discrete energy state, again this might be an excited state, and Y might fall to another level over here, the ground state. Okay, and in the process it might give off a gamma ray. So even beta particles can be accompanied with gamma rays. Now again, what we would expect from a discrete level changing to another discrete level, or maybe from this level directly over here, we might have another type of beta negative. Okay, so we should expect that the beta energy spectrum is also discrete. However, that is not the case. What we see is that beta particles have a continuous spectrum.